this area I have been working since 2007 actually. This not necessarily smart sensing, but sensor network, IoT. I also do RF harvesting, actually not harvesting but RF harvested power. RF harvesting we are working on, but if the source is RF harvested power actually, ambient RF harvesting. So source could be, this could be also another source actually. So in fact I could deploy my energy harvester module close to a base station where a lot of RF radiation is happening, and I could harvest and I could charge my battery and so on. This is one direction that we are pursuing, separate discussion. So now this smart sensing problem, what is of interest so far? So far what we have discussed is that if I am given some high rate sample data, what I can do. Okay, so I am talking about, because I don't have control over sampling, I have my basic sampling unit deployed already, and I am trying to prune the content, and I am trying to do some AIML based intelligence. Now, this is actually not sufficient. Why? Because there are a lot of applications where sensing is very hungry. Sensing itself is very energy consuming affair. So I cannot afford to sense at a high rate, consume a lot of energy there, and then again prune, consume again some energy, and then transmit. Okay, and that is the case when we are talking about wireless pollution monitoring node. We have been working on that, and pollution monitoring, actually the pollution gases that it monitors, PM, the particulate matter, is a very energy hungry affair actually. Actually, practical PM sensors have some kind of a laser module. Laser module has to be turned on, a fan has to be turned on, and so on. And in fact, we have been working on, I'm sure researchers also working on, so replacing how to reduce from laser to LED and so on and so on. We have contributed quite a lot in that. But what I'm talking about is that, so PM consumption, PM sensing consumption is very energy hungry affair. So I cannot turn on PM sensor every frequently, and as I mentioned, there is nothing called Nyquist rate, because I have a dynamic system. My environment that I am dealing with is a very dynamic actually. There is no Nyquist rate, guaranteed Nyquist rate for this. In the daytime rate changes, nighttime rate changes, etc. And likewise, carbon monoxide and any other gas sensors, these are very energy hungry affairs. So carbon monoxide, for example, current technology is that it is called electrochemical reaction based actually. So I actually created a chamber for calibration. So it's a huge affair. So depending on the concentration, so not only the electrochemical reaction consumes energy, but also the consumption varies with time. Consumption varies with the pollution level actually. So that is how the pollutants data is outcome is actually. So if the carbon monoxide, for example, I am sampling, if the level is high, it will generate more electricity, and that will be converted to my sampling value actually. And if the carbon monoxide level is low, corresponding low electricity current and corresponding. So basically these are energy hungry affairs, so I cannot actually afford to go by freely sampling and then doing it. So that is why what we want is that this ML intelligence that we have been talking about, can we pass on to the sensing stage? Sensing stage is my front stage. So so far I am dealing with this. I have my sensing, and then this is my pruning, and then this is where transmission is happening. So this is modules, that is the module that we have employed so far, discussed so far. But as I mentioned, this itself is an energy hungry affair. So if I can somehow intelligently do the sensing, then this module is not required anymore. Because intelligence is already applied here, and it will only collect the right samples. Okay, then I don't require this pruning again. But the question is, this problem is very challenging. For pruning, I have the baseline, so I can always compare whether I am doing well or not actually. But if I am not pruning, if I do not have the raw data, then who do I compare with actually? And that is where learning becomes much deeper actually. So that is the problem that we are looking at. So real life sensing environment is a dynamic stochastic process. This is one major aspect actually. and also, as I mentioned, energy consumption level varies with pollution level actually. So that also makes the problem very interesting, that the energy consumption of a pollutant, if you normally the pollution sensors that you see deployed are not necessarily multi-pollutant actually. So pollution by typically we mean that PM pollution, but in the so-called standard pollution monitoring definition, they monitor 10 parameters actually. Out of them, some of them are very energy heavy, some of them are very benign, no energy consumption, for example, temperature and humidity. So multi-parameter sensing may have some correlated nature. So again, one thing that we are looking at is the temporal correlation we want to exploit, but this is dynamic stochastic, and we also want to exploit the cross correlation among multiple parameters. Because if I have deployed a sensor node here and the sensor node has all these multi-parameter sensing capability, because it is monitoring the same environment, they might have some correlatedness, and we want to exploit that. And third thing that we are interested in is that if I deploy, and that problem actually was in our mind since several years actually. So if I deploy a bunch of sensors, let's say in a field, how do I decide the density of the deployment, spatial density of the deployment? Because of the spatial correlated nature of the pollutants actually. So some pollutants, spatial decay profile and temporal decay profile is faster. Some pollutants have slower spatial and temporal decay profile. So what that means is that if I have a multi-sensor, then I have to deploy maybe sensors in a dense fashion, but maybe sensor A has to be activated more frequently spatially, but sensor B may not be activated more spatially frequently because they are sparsely, their spatial correlation is high. Okay, so basically we are looking at the three dimensions. One is temporal dynamics, one is cross correlation, exploiting cross correlation, and third is the spatial cross correlation, spatial correlation. Spatial correlation problem we call network sensing. Actually, one PhD student had completed her defense in that direction, and that is actually much more challenging problem. And for the spatial and temporal and correlatedness, we are able to do at the node level actually. So that we have done quite significant work at the prototype development level. Okay, I think so. The closest to what I was talking about handling stochastic dynamic nature is called adaptive sampling. This is called adaptive Nyquist sampling. So one paper has proposed some adaptive Nyquist sampling. So, so they are saying that we know that sampling rate is not constant, rather process is dynamic. So kind of crudely they say, okay, every 4 hours I will decide a different Nyquist rate, like that. But yeah. So I will skip through many details here. So basic approaches is first level at the node level. Our basic approach is the node level, temporal and cross correlation exploitation. Okay, so temporal correlation is exploitation is using the PCA-based sparse signal representation, and this is a sparse Bayesian learning-based reconstruction. And cross correlation, we have combined these two later. Cross correlation exploitation is done by modified, basically started with this UCB, upper confidence bound algorithm, and Gaussian process regressor for the interpolation of the data actually, predicting the missing samples. So and then we combine them jointly to deal with both actually. So we have multiple papers, one for these, one for joint, and so on actually. This is a very nice combination. And then yeah, so I'll skip through these things. These slides I'll share and you can go through. The fundamentals of PCA and SBL, and I'll skip through these further here, and there are a lot of details here. So this SBL operates. This is actually another PhD student's work. This is what is that? Kramer-Bound. Yeah. So yeah, Bayesian Kramer-Bound is used for this SBL-based recovery technique. Okay. So yeah, I think I will skip through. Yeah, this is. So first two are to do with the temporal, then cross-correlation corresponding theory. So I will go through the main modules, actually the conceptual aspects of it. So this is some of you might be working on this bandit algorithm, multi-arm bandit. It is quite known actually right now. So basically, the implementation of this thing is actually using multi-arm bandit. Formulated that multi-arm bandit problem. So diagnostic approach that works. So the summary is that this is so we are actually now talking about the I have multiple. So in the previous module I was talking about these multivariate PMU data. So we clustered them, right? That clustering was purely based on the data correlatedness. So here, and clustering and cluster head election. Here, my cluster head election, I want to actually be a little bit more intelligent, because out of this, cluster head should be chosen which is less energy hungry. Okay, so the parameter that is causing less energy consumption, I will like to basically elect this as leader. If other parameters are reasonably close. So this is one aspect. So basically energy consumption part, energy aware clustering that we are talking about. So we have a set of sensors. We are figuring out of them some some set of sensors are called active set, and out of this active set we figure out which are to be elected to actually sample. And then within that active set, they will be they'll predict the remaining inactive set for the exploiting the cross correlation. And the multi-arm bandit comes within this active set. So active set selection is cross correlation exploitation, and multi-arm bandit now says that because they have some correlatedness, which one to be activated at what time, so that my net energy consumption is minimum and yet my sensing quality is maintained to a level. So and there is one. I will go through these papers, several of our papers. The main author here is Sushmita Ghosh. I will show you some of the papers. Okay. And then other question is that the temporal correlation is exploited in this way actually. So how far away? So we have coined a term called age of sample. Right? Age of information term has been popular in this from information theory perspective. So from our context, actually, age of sample is a very important term. So that space, your temporal dynamics is captured by that actually. So if the temporal dynamics is slow, then I call this age of sample is very low. That means it has not aged. That means I don't necessarily need to take another sample actually. So age of sampling. So question is that if I take one sample, how far away I should take up another sample actually. So if you see YD is the frequency of measurement, and D is the difference between the present and past cross correlation factor. Okay, so this is depending on, so there are many possibilities actually. So this distance versus what should be my choice, there are many factors. There is a nice trade-off on that. Okay, so we have actually referred to our old work, which actually was patented for some purpose. Okay, so and then likewise for the cross correlation based exploitation, the theory behind that also I'm going to skip. Process regression, this is very well known. There are other regression technique. Again, we chose Gaussian process regressor for our case. It suits well. I don't have any other better response here. And cross correlation based smart sensing. So that I think I have already stated that. See. Okay. So the main crux is over here. Train the GPR model, create an active set using P sensors, and then within these P sensors, which of the sensors to be picked up, and optimal sensor set using USB algorithm, send the information to the sensor node. So these two steps are being done at the edge node, and the sensor knows only which sensor to be turned on. Okay, this processing is entirely happening. This learning and processing is happening at the edge node, like this node, and this is my sensor node actually. These are the multiple parameters that are being sensed, and that's all actually. So collect the data and then predict the remaining data using GPR, and this process continues. And if the sensing okay. So okay, PCB same thing. This is with respect to the joint temporal cross correlation. I think I can skip through. Nothing much to be told further. Okay, I will try to close. Please another 10 minutes. Okay, so these are some prototypes that we have developed. Actually, this is there are a lot of innovation actually here. So how to control the hand speed, and we have replaced these thing classical. These laser-based sensors with our own developed module. We are actually further working on UV-based sensors, and so these UV-based sensors will replace these ones actually. These are very costly. So our board is costing about currently maybe total 1 lakh Indian rupees, but majorly this is because of these modules that are purchased, imported actually. This is about 70,000 is eaten up there. Rest entire processing is consuming about 30,000. So we are actually replacing that by our own UV-based sensing, and this process is actually has made the process significantly energy efficient actually. So I will give you one commercial module that we have been comparing with, that cost-wise significantly high, weight-wise this is about some few kg, maybe I think 6 kg or so. Our module is about 700 gram. And this is consuming, this is actually operating using solar panel, and in contrast, so this is currently consuming about 50 milliampere current, and which is sufficient drawing from this thing. 72-hour backup capability by this battery we have. And in contrast, the module that we have comparing with commercial sensor, multi-sensing capability, is consuming 2.5 watt, which requires a power supply. Regular power. So these are the sensors that are being monitored actually. So PM2, PM10, and so on, temperature and humidity and yes, these are being collected in IoT server. So the last module, okay, so this is second last module. So this is about network sensing. I quickly run through without going into much depth here. So do we really need so much data? Can we acquire less than what we need, and then exploit correlation? And okay, so quickly go to, I think I will go into this module. These are the 4 different modules that you have contributed. One is centralized adaptive sensing framework. These are all network sensing. So I was talking about now if I have deployment, and how do I activate the set of sensor nodes, and then within the set of sensor nodes, which sensors to be activated. These are the crux problem. So in the multi-sensing framework, and that problem is divided into, first we tried with centralized version, then a decentralized version, and then these are to do with single sensing capability, then a multi-sensing capability with centralized version and decentralized version, and then this is the work that I was talking about with respect to the age of sampling concept that we have introduced. Okay, I think I will skip through these details. Again, look at the slides, look at the papers for more details. This is for centralized sensing. So centralized sensing concept that we initially thought is that if I have we formulated this as a one-dimensional problem, and if I have a bunch of sensors and if there is a pollution source, also our motivation of this exercise is actually indigenous. So in India, what we have is that we know what is the average pollution level. Okay, so very, very bad, right? Delhi pollution level goes up to as bad as 500. Okay, but what we are interested in our work, what we are interested in, can we develop small miniature pollution monitoring nodes which can be deployed at a mass scale, less energy consumption and less cost, so that they can localize the source of pollution. Okay, because average pollution we know already. So, but we want to pick up the culprits who are actually generating pollution. For example, in the morning hours, all the people who are brewing and dusting, they are creating a lot of pollution. In campus, we have actually told them many times. Actually. Likewise, there are people who will do the, let's say, some services company will have to fix the electricity. They will dig the road. They will not properly cover and so on actually. So we want to deploy these sensors, and there are, for example, dump yards where there are a lot of gas pollution is happening. These are very unhealthy actually, and we have actually deployed a mobile sensor in Hyderabad, one place. This problem we have been working since many years. So to summarize here, we are interested in localizing the polluted sources actually. So that is why we are interested in miniaturizing pollution sensors, and the cost is so important and energy is so important. So here the question is that if I have a bunch of sensors deployed, let's say this far away from the pollutant, how do I activate this set of sensors? And considering their remaining energy is randomly varying, and also I want to create a pollution map of that locality in a one-dimensional scenario, and that is extended to two-dimensional scenario also. And here we are claiming that all the sensors are there is a centralized data collector which will collect all the data. But it could be questionable that the centralized data collector could be actually far away, and then this could be consuming a lot of energy in transmitting the data. So we have considered a data mule concept, that maybe someone will go in a backpack and collect the sensor data. So sensor data collection is not necessarily very energy hungry here, just to motivate the centralized problem. And decentralized problem is that motivation does not work always. So if I have a bunch of sensors, can we now create a cluster, or how do I do clustering, and how do I re-elect the cluster heads, and so on. Okay, so these joint optimization of sensing quality and energy efficiency, and provide energy balance among the sensor nodes. There is no dedicated cluster head. We are considering among the sensors, set of sensors, someone could be elected as cluster head, and that process will continue, and so on. There are many variants of electing this thing, and we have shown which works best, etc. Skip through again. This is the further detail how the cluster heads work. And finally, multi-sensing, as I was talking about, these problem definition I gave, it is actually exploiting the spatio-temporal and cross-correlation profile together. Again, I skip through. And I think that's all actually. Okay, so and finally here we have so one problem that I have not discussed here is in the context of smart sensing. The smart sensing capability is actually allowing us to do another very interesting thing, that now when I am sampling data, I am not only bothering about my spatio-temporal correlation and then deciding what to collect, but also I can now, because I am deciding what to sense and when to sense, I might be leisurely sensing some parameter, and then if that parameter is otherwise critical, for example, I have a health heart rate is being monitored, and suddenly if my heart rate certainly generates wrong data, this sensor attached should be able to adapt that certain value has crossed certain threshold, and then I need to sample at a higher rate possibly. So what I mean is that data-driven sensing. So now, because my smart sensing actually allows me to do that, actually we have incorporated simple Markovian model we have applied here. You can look at that paper, and data-driven sensing, and this problem is having very deep connect further actually. So data-driven sensing, now data-driven access, data-driven routing, and so on. How do I prioritize? For example, the node that was generating very rudimentary data suddenly has become very time-critical data. So my entire network end-to-end has to be very adaptive to provide resource at the access level, at the routing level, and so on. This is very interesting. Okay, I think I'll skip further. That is what I was talking about, the smart sensing paradigm. These RT, NRT. So classically we designate this is RT data. This node is generating non-real-time data. It is nothing like that actually in the today's context. So data generation, real-time or non-real-time nature of the data can vary, and not only that, this data real-time or non-real-time nature can vary along the traffic flow also. So for example, I have a time budget on a data. Okay, I transmit the data, and then this data has to be delivered within the time. I see that time budget is good, so I relax initially, and then suddenly I see that I have very less time budget, so I have to actually be very critical now. So as it progresses, it could be possible that the data critically changes. It could be other way around. Initially, I acted very hurriedly, but I am almost close to the destination, so I can go lazily. So like that. Okay, so that is the result. So summary. So this is one thing that I wanted to take away here actually. So what we discussed so far is called context-aware smart IoT. I have taken some examples only, and if I have backward compatibility requirement like smart metering, PMU, and so on, then I go by this. If I have clean slate design approach, then I can do much more actually. Of course, this is more challenging. AI, learning, etc. has been invoked more deeply. But then I can actually do customizable real-time, non-real-time design solutions, data-driven dynamic priority adaptation at the different levels. That is one thing. And there are some references. There are many papers I have just not possibly updated. The other thing that I wanted to do is very quickly, maybe 5 minutes, not more than that, is that we have been actually putting a lot of effort in translating some of our prototypes. And what we have, this is our recent introduction actually. So this is what we call ourselves actually. And this is what is the users. So for example, our, let's say, industry is this community. This is the people who are actually industry developers, and these are the industry users, and these are us, the core researchers. Okay, so so what we mean is that, so basically trying to facilitate the research translation ecosystem and more useful technology driven research actually. So these people are helping us in terms of picking up what can be translated, and these people are giving us input on what is of interest from their perspectives actually, and trying to create a conglomerate of that actually. And this is actually a challenging task. What happened? Yeah. So we and this problem that we had to handle, because see the IoT research that we have been doing, and I have shown some translation, because this does not require huge resources. So this, if we are dealing with, let's say, 5G and beyond 6G systems, we need actually some most capable implementers. So one problem at the first module I mentioned that we have come up with these learning, what is that called, your channel availability sensing technique, but implementation has to be more efficient to actually make it useful, and that implementation has to be at the FPGA level, which our conventional communication researchers cannot do it. So we have developed some setup with the help of engineers, and they are modularizing and so on. So we have access to these modules. For example, one we are keeping for anything that we want to change here. One is kind of ruggedized for making some kind of a different applications driven research and so on. And then correspondingly smart IoT also, we have been working on different translations, and the translational challenges I have not explained further, I will skip through, we can take up further. And some more work that we have been doing, where also there are significant potential of learning. I was talking about these energy harvesting. Actually, I have been working on these problems many years actually. So beamforming, distributed beamforming, and how to, let's say, do this. This is a very difficult problem. We have some research to skip through. And these learning aided spectrum sharing and coexistence, their learning is very deep actually, quite challenging learning required. Currently we are looking at transmitter and receiver and capabilities, but ultimately the adaptive learning has to happen at the transmitters efficiently, so that we can adapt the transmitter's capability of transmission and reception. Skip through this. This is another thing that we have been pursuing, AI-aided mobile integrated sensing and communication from multiple perspectives. We have some publications that are coming up, and also these things. Let's skip through. And this is what we have in our research. Okay, I think I will close.